Okay, so for 13, we treat it like a quadratic, correct? Because we have an x to the fourth, an x squared, and 3. And if you remember, I proved it to be true, where we broke it up into ax squared plus bx plus c. Okay, in any case, we treat it like quadratic, so therefore we use MAG to factor our MAF. So everyone agree with that? Okay, so you treat it, you just think of the x to the fourth like our x squared term, and our x to the second like our x term, and then we multiply to be 3 and negative 4, okay? Okay, so when multiplies to be 3 and adds to be negative 4 is negative 3 and negative 1. Now instead of the factors being x, they're going to be x squared minus 3 x squared minus 1 equals 0. Why do we know they're going to be x squareds? Because if you think about it, you FOIL it back out, that would give you x to the fourth, and you add your middle terms, it would give you x squared terms, right? Okay, so now we set them equal to 0. I set the first one equal to 0 and move over the 3. I get x squared equals 3, correct? Square root gives us x equals plus or minus root 3. Now the other one, x squared minus 1, move over the 1, and then square root. That will give you x equals plus or minus 1. On this one, when we have denominators, you agree we want to get rid of the denominator. So with equations, we know what we do to one side, we can do to the other. Given the fact of the room on the left, I'm going to write on the right-hand side. We want to get the LCD of the denominators, which means we want to multiply something that will cancel out all the denominators. It's not as clear when we have binomials with variables like this. So we simply, for instance, if it's 2 and 4, we just know we multiply by 4. Much easier to work with. So in this case, you go denominator by denominator. If I have x plus 1 in the first denominator, what do you have to multiply to get rid of x plus 1? X plus 1, right? The second denominator, to get rid of that one, would be x plus 2. And then we look at the third denominator, which is 1. 1 over 1's 1. So there's nothing to multiply to get rid of that one. So our LCD is x plus 1, x plus 2. Okay, so now when we distribute in, I suggest that you don't cancel literally by hand. When you distribute in, you're distributing that whole term, x plus 1, x plus 2. Because on the next time when you multiply, you may forget that if you literally cross one of these guys off, you may forget that you're supposed to uncross it for the next problem. If necessary, write it over on the side. But in any case, when we distribute in, look at what cancels. What cancels in this case? The x plus 1's. So now we have 4, that didn't cancel, and an x plus 2. Now, with this negative here, I would suggest distributing the negative to the 3 in the numerator there, because we're subtracting everything in the numerator. And now, when we distribute this in to the second one, what's going to cancel in this case? The x plus 2's. So we still have the negative 3 and the x plus 1. 1 is simply, times that is simply x plus 1, x plus 2. So the 1 got complicated, more obviously, but ultimately the problem's much easier to work with. Okay, distribute the 4, the negative 3, and over here we want to FOIL, distribute, because ultimately we're going to have a quadratic, and to solve quadratics we have to be set equal to 0. Set them all equal to 0, so we're going to get 0 on the left-hand side. Does everyone agree with that? The x squared term, we only have one x squared term. If necessary, with a bunch of terms, go ahead and cross it off. The 4x minus 3x on the left would give us what? 1x. So I have 1x over here, and I'm subtracting over the 1x. Combined with the 3x will give you 2x. So 4x minus 3x gives you x. Subtracted over gives you 2x on the left. We have 8 minus 3 on the left, which gives us 5 on the left-hand side. Subtracted over gives us negative 3. Okay, MAG, what multiplies to be negative 3 adds to be 2 would be x minus 3, x minus 1. Do we agree? No. No, that's incorrect. There we go. Positive 3 and negative 1. Which will then give us, whoops. And get rid of that 0. Here we go. X equals, set them both equal, 0 and solve. You get x equals negative 3 and positive 1. Note, from the beginning, I would suggest, you don't have to do this, but from the beginning, to help yourself out, you can write that x cannot equal negative 2 and negative 1 as you go through this, yes, inconvenient problem that it is. And we have a bunch of work at the bottom. Our solutions can make the denominator 0, correct? So if you put x equals negative 1, negative 2 over on the right-hand side from the beginning, you don't have to do that, but that'll be a cue to you. Then the quote-unquote eyeball check, you just have to look. Is negative 3 and 1, is that negative 1 or negative 2? No, it's not. So are these possible? Yes, they are, and your solution is negative 3 and 1. Okay, 69 from 1.6. The mechanics of absolute values. On the left-hand side, we always drop the absolute value bars. Are we in agreement? And then on the right-hand side, you don't have to write this step. I apologize, that's supposed to be a plus sign. It's a little better. Plus or minus the parentheses x squared minus 5. If we think of x squared minus 5 as a number, the absolute value is going to be equal to the positive and the negative of that number. Okay, now we set up the two equations. Note, if you can go straight to setting up the two equations, more power to you. If not, you do that. And then over here you get x plus 1 equals the opposite of all of that, which would be negative x squared plus 5. These are quadratic, so we want them set equal to 0. It's preferable to have our a term. It's positive, correct? So for the left-hand equation, I'm going to move everything to the left-hand side because x squared has a positive coefficient. Negative x minus 6. Factor multiplies to be, let's make that a 0. Negative 6 and adds to be negative 1 would be negative 3 and positive 2. And then set them equal to 0 gives us x equals 3 and negative 2. Okay, any questions? Now, when you plug these back in, positive 3 and negative 2. When we plug that back in for absolute values, this left-hand side, that is the distance the number is from 0, the number inside the absolute value. So this number out here always has to be 0 or positive, correct? So when you plug in 3, you are eyeball checking. If you plug 3 into the right-hand side here, will that be positive or negative? It would be positive, and therefore 3 is possible. If you plug negative 2 in for there, negative 2 squared is 4. 4 minus 5 is negative 1. Can an absolute value equal negative? No, it can't, so you simply cross it off. And that would be full credit for that part of it. On the right-hand side, the right-hand quadratic, negative x squared, your x squared term has a negative coefficient, so let's move everything to the left-hand side. If I move the x squared over, that would be positive x squared. I'm keeping the x term there, and then move over the 5. By subtracting it, gives us negative 4. This is not factorable. Multiplies to be negative 4, adds to be 1. So we use quadratic formula or completing the square. Opposite of b, plus or minus square root b squared, which is 1 squared, which is simply 1, minus 4 times a, which is 1, times c, which is negative 4, all over 2 times a, with 2 times 1 is simply 2. So we get negative 1, plus or minus 2 negatives turn positive, so you have 4 times 4 is 16, plus 1 gives us root 17 all over 2. Those are your other solutions. To make sure that those work, we would have to plug them back up into here to make sure that it makes it positive. That's a drag. And I know you know how to do that, but I'm not expecting to do that for full credit. One of those may not be correct, but don't concern yourself. When you have non-whole numbers or non-real easy fractions to plug back in, that's kind of a wicked fraction. You've already been tested on how to do that with those. So if you get an irrational solution for a quadratic, I'm not expecting you to plug it back in. Next part, this goes back to 1.5 with the powers of I. Remember, I is equal to I squared is equal to -1, I cubed is equal to -I, and I to the fourth is equal to 1. If we continue that pattern, or excuse me, if we go I to the fifth, I to the sixth, and so on, that pattern simply repeats itself, correct? So, that pattern repeats itself, which means it breaks down the exponents into divisions of 4. So if I have I to the 45th, for instance, you want to find a multiple of 4 that is just less than 45, which would be I to the 44th. When it's above 40, you can help yourself out by simply going to 40 and then counting from there. Okay, so we have 4 more from 40, so we have I to the 44th, and then I times I to the 44th times what gives us I to the 55th? We add exponents, so that would be I to the first. I to the 44th gives you 1, I to the first is simply I. So any of the problems, you simply find the largest multiple of 4 just less than 45. Okay? Okay, so now that I'm recording, negative on the inside, distribute, and then combine like terms. 8 and -4 gives us 4. That root 18 would have been preferable to break this down at the beginning, but I didn't. Fallible. We have root 18 is now root 18I. We don't know, I think conceptually we don't know how to work with root negatives, but we know how to work with positive roots as well as I, correct? Can root 18 be broken down? Yes. Into 9 and 2, which gives us 3 root 2I. Can the I be put out in front of the radical? Yes. So now I have 4 plus, you can think of it 2 ways. Root 2I is your variable. If root 2I is your variable, you have 3 of them plus 3 of them, which gives you 6 of them. So this is still plus. If 3 root 2I, all of that is your variable. If you have 1 of them plus 1 of them, you have 2 of them on the outside. So that would be 2, 3 root 2I. If you think of all of that as your variable. And then if I have 2 times all of that, we can combine the 2 and the 3 to give us 6. It gives us the same in either case, depending on what context you put in as far as what the variable is, okay? So your final answer would be 4 plus 6 root 2I. And that's your standard complex number form, but I is also preferred to put out in front of a radical when we have one so it doesn't look like it's underneath the radical.